Fourier transform or complex Fourier transform. So definition: Fourier transform or complex Fourier transform. Let f of x be a function defined on minus infinite to plus infinite open interval, that is the real line, and be piecewise continuous in each finite partial interval. Suppose if you divide the real line, for example, you take a1 b1 is an interval, a2 b2 a3 b3, like that. In each interval a1 b1 a2 b2, the function is continuous. Each pieces, right, a1 b1 a2 b2 a3 b3, the function f of x is continuous. Maybe it function f of x may be discontinuous at the end points, like a1 at a1 at b1 at a2 at b2, the function may be discontinuous. Then it is called piecewise continuous, right? So definition: a piecewise continuous function is a function that is continuous on each of its pieces but may have discontinuities at the endpoints of the pieces, and absolutely integrable in minus infinite to plus infinite. In the real line, the function is absolutely integral. Absolutely integral means Lebesgue integral, that is integral over the real line of modulus f of x dx is less than infinite, that is a finite value. Otherwise it is convergent. All three are same. Absolutely integrable, that means integral over real line modulus f of x dx is a finite, or it is less than infinite, or it is convergent. Right, that means the function f of x is absolutely integrable in the real line minus infinite to plus infinite. Absolute integrable function. If a function is for a function whose absolute value is integrable over a specific time of interval, right, is finite, then it is called absolute integrable function over a period. That is integral minus infinite to plus infinite modulus f of x dx is finite or less than infinite, or it is convergent. Then Fourier transform of f of x, that is capital F of small f of x, which is equal to 1 by root 2 pi integral minus infinite to plus infinite e power I px f of x dx, which is called Fourier transform of f of x. It is denoted by f bar of p. The function f of x is called inverse Fourier transform of f bar of p, right? Capital F denoted by the symbol, right? Capital F denoted the Fourier transform of a particular function small f of x, right? That means that inverse f inverse of f bar of p, right, which is equal to f of x. That is, f of x is called the inverse Fourier transform of f bar of p, right? Capital F of small f of x, which is equal to f bar of p, right? In similar manner, f of x is equal to f inverse of f bar of p, right? Next, Fourier integral formula. F of x satisfies the Dirichlet's condition in every finite interval minus L to plus L. Dirichlet's condition. There are three conditions under this. First one, the function must be periodic with period and absolute integral over a period. Second one, the function must be piecewise continuous and piecewise differentiable and bounded variation in any given bounded interval. Third one, the function should have a finite number of maxima and minima in any given interval. So if a function satisfies all three conditions, then the function satisfies the Dirichlet's conditions. Everything explained in the Mellin transform, right? Part 1, I think so, right? Okay, we'll go to the Fourier integral formula, and defined as 1 by 2 f of x plus 0 plus f of x minus 0 at every point of discontinuity. Further, if integral minus infinite to plus infinite modulus f of x dx is convergent, that is f of x is absolutely integrable in minus infinite to plus infinite, then f of x is equal to 1 by 2 pi integral minus infinite to plus infinite f of v integral minus infinite to plus infinite cos omega x minus v d omega dv, or f of x is equal to 1 by 2 pi integral minus infinite to plus infinite d omega integral minus infinite to plus infinite f of v cos omega x minus v dv, or f of x is equal to 1 by 2 pi integral minus infinite to plus infinite f of v integral minus infinite to plus infinite e power I omega x minus v d omega dv. This is the Fourier's integral formula. So there are three forms of this formula. So first one, f of x is equal to 1 by 2 pi integral minus infinite to plus infinite f of v integral minus infinite to plus infinite cos omega x minus v d omega dv. Second one, we are just splitting the integral. First d omega, then f of v cos omega x minus v dv. Right? We split the integral and with the integrand. We splitted omega and v. Then last one, we converted cos in terms of e power, right? E power I omega x minus v d omega. So three forms of Fourier's integral formula. See, I'm not going to prove this, right? I'm not just I have stated the Fourier's integral formula. So we will see the proof at the end of Fourier transform, right? We'll try to see, right? Thanks.